Well, hello again, and this is day 2 for pre-algebra summer prep class. And if you remember from last week, we talked about exponents. We talked about different rules of exponents. For example, anything to the 0 power is always equal to 1. We talked about negative exponents, which really didn't have anything to do with the number becoming negative, but instead it made it its reciprocal. And we talked about the property of products, which means if I had any number with the same base, an exponent, and multiplied by another one with the same base, and either a similar exponent or a different one, they were multiplied together, what we actually did was ended up adding the exponents, and then obviously with dividing, we ended up subtracting the exponents. If any of that sounds vague to you, you can go back and watch video 1 as we talked about that in depth. But for video 2, we want to finish up our last property of exponents that we need, and that is called the property of powers. And in the property of powers, it's set up just much like this. We have x is our base number. X is already to a power of m. Well, we also took that whole entire base in exponent and put it to another exponent to the power of n. And we call that the property of powers. And what happens in that is our base then gets set to m times n. Or another way to write that, then if we were to take this and put it in with some numbers, it might make more sense to you. And if I had to say x to the 4th and all of that to the 3rd power, then I would end up with something that looks like this: x to the 4th times the 3rd, which then equals x to the 12th. The reason that makes sense is that because this 3rd power is saying that everything in here, it gets multiplied by itself 3 times, so that's really representing x to the 4th times x to the 4th times x to the 4th, which then, if I know from last week, x to the 4th times x to the 4th is x to the 8th, times x to the 4th again gives me x to the 12th. And again, that's the basis of what we talk about with the property of powers. So we can use that information. I'm going to go ahead and erase, and hopefully you've got that written down. If not, you can pause the video and get there. But if I was to say I've got something like 3x squared to the 2nd power, and I want to divide that by, let's say, 2 x to the 3rd to the 3rd power, I would first of all start on top. This 2 affects everything inside the parentheses, so I actually am going to take 3 to the 2nd power times x to the 2nd times the 2nd, all of that over 2 to the 3rd power times x to the 3rd times the 3rd. Well, 3 to the 2nd power becomes 9, and then the x, 2 times 2 is to the 4th. Down here, 2 to the 3rd power is 2 times 2 times 2, which is 8. So that becomes 8 x to the 3 times 3, which is x to the 9th. If I want to simplify that in a different form, then I can say that my answer, I'm going to bring it down here, is 9/8, and this would be x to the negative 5th. If you remember from last week, when we subtract exponents because we're dividing and we subtract them, we end up with 9x to the negative 5th over 8. Or guess what, there's even another way to write this that we haven't talked about a whole lot. That would be 9 over 8x to the 5th as well. Okay, and again, that's just a brief description of powers, and you will see this on some of your work that you have in front of you. The other thing we want to talk about is scientific notation, and many of you hopefully know a little bit about scientific notation. It's what, guess what, scientists use to write really, really large numbers or really, really small numbers so that we don't have to write them all out. For example, if I have the number 3, 6, 0, 1, 2, 3, 1, 2, 3, 1, whoops, 2, 3, I end up with 360 trillion. I'm not going to want to write that, especially if I have to multiply it by something or something along those lines. So what I want to do is I want to put that into what we call scientific notation. And all it's really doing is breaking it down into something we can multiply by a power of 10. With scientific notation, a really important point is that scientific notation can only have one single digit to the left of a decimal. So if I actually look at this question here, or this number right here, the reality of it is it has an invisible decimal way down here at the end. We don't talk about that much because we don't have anything after the decimal, so we generally leave it off, but it's there nonetheless. If I want to look at this and say, well, scientific notation means I can only have one number to the left of the decimal, that means I need to move this one 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 spots over. That ends up giving me the number of 3 6/10. And if I have 3 6/10, I'm going to multiply that now. Because I moved this over 11 spots, I'm going to have to multiply that 3 6/10 times 10 to the 11th power. And because I've done that, now what I really have taken is I've taken 3 6/10 times 10 would be 10 trillion in this case. And so this becomes my scientific notation way of writing 360 trillion. And as you notice, it's a much smaller way to condense that number. You will sometimes see this if you look on your calculators, and sometimes you'll get really large numbers where you have maybe an E at the end. Well, that E represents the number 10. So the opposite can work for this. What if I'm given something that's already in scientific notation? And let's say it says 2 9/10 times 10 to the 5th power. Well, I can write my number, 2 9/10, and now I know that my decimal has to move 5 spots. So it's going to go 1, 2, 3, 4, and 5. Well, there's nothing there. Another name for nothing is 0. And so I'm going to put those zeros in. That means I've taken my decimal and I've moved it all the way over here. So putting it back into standard form, my answer then is 290,000. And that's how we can convert those back and forth. Now the same thing works if we have a really small number. If we have a really, really small number, for example, we have 0, 0, 0, 0, 0, 0, 0, 0, let's say 3, oops, get rid of that decimal, 3, 7. Okay? I don't want to have to write that a bunch of times, so I'm going to come up with the same idea to solve it with scientific notation. And if I look at this, I can, again, have only one number to the left of the decimal. Well, if I look at this, all it has is a 0. Well, 0 is really nothing, so I don't want that. What I want is an actual number besides 0, and that's all the way down here. So I'm going to take my decimal and I'm going to walk it down again. 1, 2, 3, 4, 5, 6, 7, and 8. And I'm going to end up with a number that is 3 7/10. And then I think to myself, how far did I go to get down there? I moved it 8 spots. In other words, I multiplied it by 10 to the 8th power, which means it went in the opposite direction, so it's going to become a -8. We talked about negative powers the other day, didn't we? So now, again, can I go back the opposite way? What if I had something like 4 and 5600ths times 10 to the negative 6? Well, that's going to give me 4 and 5600ths. But now it says I'm going which direction? I'm going to have to move it 6 spots this way. 1, 2, 3, 4, 5, and 6. I'm going to put my decimal there. 0, 0, 0, because I have nothing there, right? 0 and 0. Now I get rid of the decimal there. My new number looks like this. So this is scientific notation. Many of you hopefully have had some of that. I know depending on which teachers you've had over the last year or two, you probably would have done something with scientific notation. Now the reason that's important is because now we're going to join in kind of what we did when we had the exponent rules. So now we're going to take something that looks like this. 2 and 1/10, we'll say, times 10 to the 5th times, let's say 1 and 9/10 times 10 to the 7th. And if I look at something like that, okay, I could, if I wanted, rewrite this problem as 210,000 as 210,000 times, and I could look at this as 19123 as 19 million, and I could multiply those, and then I could convert them back to scientific notation. Or, kind of the beauty of this is I can take my two front numbers, because again I have one spot to the left of the decimal, and I could multiply them. I have 1 and 9/10 times 2 and 1/10. That gives me 9. That gives me 1. That gives me 8. Carry gives me 3. I end up with 9, 9, and 3. 2 decimal spots, I move it over. So what I end up with is 3 and 99/100ths. Well, I'm not done because I still have my 10 to their certain powers. Well, this should look familiar because now I have 2 10s are both the bases. So I'm going to multiply it times the base of 10. And when I have the same base and I'm multiplying exponents, remember what we do? That's right. We add those exponents. So this becomes 3 99/100ths times 10 to the 12th power. Now you can see where our exponent rules are starting to come into play again. Okay? Let's try a couple more. And again, at any point, please go back through and rewind the video and follow along again. It's going to be helpful. What if I ended up instead with something like this? 4 and let's say 13/100ths times 10 to the negative 8. And I want to multiply that times, we'll say 1 and 6/10 times 10 to the negative 9, we'll say. We'll go way out there. So those are both really small numbers. And so, again, I wouldn't want to write those all out and try and multiply those together because that would be really, really time consuming. So what I'm going to do instead is take my front numbers, and notice both of them have just one number to the left of the decimal. One number to the left of the decimal, even though this one has 2 after, which is fine. We're going to multiply those together. And if I multiply across, and then this gives me a 3, 1, and a 4. And then I have 3 decimal spots, so I'm going to move it over. So my answer is 6 and 608,000ths. Okay? So again, I bring that up over here. 6.608 times, notice I still have a base of 10. I have a multiplication of exponents, which means I add them. Negative 8 plus negative 9 is a negative 17, and there is my answer. Hopefully that makes a little bit of sense to you as we are combining and multiplying exponents. Now, one more we'll try. What should happen if I end up with a problem such as 9 and 1/10 times 10 to the 15th, we'll say, and I multiply that by 5 and 5/10 times 10 to the 20th, we'll say. So really huge numbers. And when I go through to solve like I normally do, I'm going to say 9 and 1/10 times 5 and 5/10. I'm going to multiply through. I'm going to multiply through. And I'm going to add. And I end up with a number like that. And now here's my number, 50 and 5/100. Then I'm going to bring out and I'm going to multiply times 10 to the 35 because I add the 15 and the 20. That's a huge number, isn't it? But if you notice, there's something wrong with my problem. Do you know what's wrong with my problem? I have more than one number to the left of the decimal. So I'm going to have to move that over, which means I change this from 50 to 5. That means I change this from a big number to a smaller number. And if I do that, I'm going to have to change this because this went smaller. This is going to have to go bigger. And I'm just going to rearrange my numbers by my decimal, and that will give me the same equivalent. And now it's in scientific notation because there's only one number to the left of the decimal. I hope that makes a little bit of sense to you. Again, watch them over and over again and try and follow patterns that we have. Scientific notation used for really large numbers or really small numbers. We don't need to know them inside and out, but we do need to be comfortable with transferring them from standard form to scientific notation, and as well as being able to multiply two scientific notation equations together. Hope that helps, and we'll see you soon.